technical art. So please join me in welcoming Andrea.
Hello, everyone. Yep, exactly like they said. This is a talk about learning to think like a tech artist. Now, let's see here. Yep, there we go. So my very first slide is exactly what you just said. I had no idea you were going to introduce me, so this is all prepared. We're going to just go through that real quick. Again, I'm a trans woman. My name is Andrea. I'm a tech artist. I've been in games for 13 years. And exactly like you said, I am currently working on Valheim, doing all kinds of things. I was hired as a VFX artist. And it turns out when you work at a 14-person company, you can do a lot more than just what you get hired for. So now I am one of 2 programmers on Valheim. This talk is mainly aimed at students and juniors and anyone else who is new to games. But it's also aimed at anyone in any other field in video games who's curious about how tech art works, the inner workings of it, or if you just want to understand what happens under the hood of the games that you're working on just like a little bit better. And I believe that when you know how things work, you can do your work better. The talk is going to be structured in levels. I'm going to take you from the very basics of tech art, absolute basics, things that any 3D artist knows, and we're going to take you all the way to the top. And hopefully along the way, you're going to learn to see models, and you're going to learn to see textures in a whole new light. Start with level 1, the basics. So, models. I think you all know what a model is, right? Yes, okay. Be weird if you didn't. Every model you see is a file with a shape in it. Every dot that you can see on the scan is a vertex. Together, they combine to create a 3D shape. All the vertices on here connect together to form polygons, more specifically triangles. You can do other shapes when you're rendering models, but they're not really relevant today. And in games, 99% of the time, you will be rendering 3D like triangles. If you have N-gons, you're working somewhere else very specialized, probably. Textures, it's an image. I think you all knew that. You can put on that shape. It's made from pixels. A pixel is made from 3 values usually, red, green, and blue. Sometimes an alpha value as well. Alpha being used for things like transparency or, if you're making a window or you're making a glass, you probably have a low alpha value, right? Pretty classic. You might sometimes store how shiny a model is in the alpha mask of the texture as well. So the texture is normally applied to your model using a UV map. They are, if you're a 3D artist, you'll be intimately familiar with these and how absolutely boring they are to make. The information is, of course, stored in your model. Basically, every vertex in your model, all those little dots that we were looking at earlier, they store information about where on the texture that vertex places itself, right? So you can see that transformation here, where it goes from the UV map to the model. It's that kind of thing where it's just mapped into a 2D plane. It might help to think of them like a bearskin rug. Just like how a bearskin rug is an unfolded bear, a UV map is usually an unfolded version of your model. Nothing complicated. Slap a texture on a model. Very standard. You've all seen this. But let's get a little more complicated with it. What other kind of information do we store in models and textures? Shading. Very important. I think we use this all the time, actually. You might have noticed that most modern games have lighting on their models. To do shading, we need to know what direction the surface is pointing. so we can compare it to the direction lights are pointing and do a bunch of scary math to make things shiny, literally. So that's why we have something we call normals. Okay, give me hands up for who here knows what a normal is? Okay, who here knows on a technical level what a normal is? It's okay, it's not bad, not bad. If you don't know the math term for it, it really just means the direction directly away from the surface. Sorry for the very spooky, hairy bust here. Yeah, the direction away from every vertex, directly away from the surface of the model. We store the information about this normal in every vertex of the model. They're stored as a normalized vector. That means a vector with a length of 1. Math terms. I can't really go much deeper into that. There's good videos about that online. It's a common way to describe a direction, basically. Every little stick on this model represents one of those normal vectors. So normals can, of course, be extended into the other realm that we're talking about, textures. And we call those normal maps. I think you've all seen a normal map like this before. Very familiar? Oh, it's a lot bluer on that screen than it should be. That's interesting. A normal map, they are basically a texture that tells the rendering engine, hey, we should rotate the direction of the normal on this model just like a little bit when you render this pixel, right? And that means we can do even fancier, more detailed shading without increasing the complexity of your model. So this texture is a little bit special because unlike the base color texture from the previous layer, the color texture is just an image. You're used to what an image looks like. You know that you get the same color out. When you put this image into your game, every channel stores different information. It's a very important technique that is kind of key to the entire thing that I'm talking about today. It's also a technique that we're going to use to save on texture memory, for example, by packing other kinds of information into your different channels of your texture. By packing maps together like roughness or metalness or ambient occlusion into one texture. Everyone's done this, I'm sure. That's where we're getting to now, basically, with the anatomy of a normal map in level 3. So, every normal map has data in 3 channels: red, green, and blue. Red over here has data for rotating the normal in the x-axis, that's left and right. Green has data for rotating the normal in the y-axis, up and down. And then blue is a little more complicated. It's not actually super important right now. Generally, the data that's in the blue channel here is actually thrown away and calculated on the fly because it's well, I'll explain what it does in a moment, but it's just not really necessary to construct the information we need. I think it's mainly there to make the image look good at this point. So, to take this a step further, the first big key to seeing an image as data instead of a texture. A fun and important trick here is that there's absolutely nothing that says you have to treat the red, green, and blue channels of a texture as colors. They don't have to be red, green, and blue. We often just mark them as X, Y, and Z. They just look red, green, or blue when you open an image. The way the computer sees it, it's just 3 values that range from 0 to 1. So what's really stored in that normal map is actually a normal vector. Just like what I talked about in the model before. It points in a direction depending on the information in the image. There are a few problems with this. You remember how I said that a normalized vector has a length of 1? Well, this is too long. The other one here is that if all the numbers are between 0 and 1, that means you can't have negative numbers. You can't get a normal that points to the left. You can't get a normal that points down. A normal that points fully left would be -1, 0, 0. One that points fully down would be 0, -1, 0. And yeah, I don't know if you've looked at PNG files lately, but I've never seen a negative color in them. They can only store positive values. But what we do is just pack this into the files with some very simple math to take care of both of these problems. All we have to do is multiply the value by 2 and subtract 1. The way we do this, or the reason we do this, is because doubling the value brings the length of the vector into the 0 to 2 range. It gives us the full range of the normal, and then we subtract 1, and that brings it back down in the to the -1 to +1 range. And now our vector is unit length, which is another term for a length of 1, and it can point in any direction, as you can see here. If you're really, really smart, you might have also figured out what the blue channel in the normal map from earlier does at this point. It is the remaining component of the vector that you need to make it unit length, essentially. Some more complicated map happens to apply this normal vector to the rendered pixel, but that is another talk entirely, and not entirely important to this one. So let's take it one step further and talk more about colors as numbers. So, to recap the last level, textures are essentially just a big spreadsheet of numbers. The UV position on your model is what tells you which part of the texture to read, and the output you get is one number per channel. What actually determines what those numbers do is the shader that renders your model at the end of the rendering process, right? A regular shader, the standard shader that you see in Unity or Unreal or anything else, will take a color texture and some extra other textures and inputs, apply some lighting, and then output that color to the screen, right? But like I said, colors are just numbers. So what if we treat the color texture as a vector instead? Well, we can start to do all sorts of fun math. You might have heard the term color space before, right? It's actually just very literal. When you map red, green, and blue to X, Y, and Z, like in that cube, that's exactly what we get, is a color space. So we can, for example, compare the distance between a color in an image and the colors in a palette, find the closest one, and select it. And now we have a palette mapped image. It's literally just comparing the distance between two vectors, treating the colors as if they are positions in space instead of just a color, right? So palette mapping is not more complicated than that, and this kind of stuff, when you start thinking about it, it means that all kinds of interesting effects with colors, if you just stop pretending they're colors, you can do all sorts of fun stuff with it. Another fun example is by comparing our color with the relative luminance of sRGB values using a dot product operator. We can make grayscale images. I use this one all the time for lots of different effects because it means that I can quickly create a grayscale mask, or like a single channel mask from a 3-channel image. So I can use this to put extra effects on anything that already has a color image, but limit it to certain parts of that image by turning it grayscale. So let's move on to one of the final levels. Not quite the final one, but level 5, talking about models as storage. So we're adding in an extra dimension here. Because models can store a lot of interesting data. They have vertex positions. They have UV channels. There are at least 4 of them. It depends on the engine and file format. Unity supports up to 6 channels. Most common use for UV0 is obviously mapping your texture to the model. Most common use for UV1 is putting your light map data in there, but then you can keep stacking those UV channels. Technically, they're UVWZ channels, but most model formats don't support 4 channels in the export, and most engines don't support 4 channels in the import. But if you generate your models on the fly, you can put in even more data in your UV channels. You also have vertex colors. They can be used just straight up colors to tint stuff. This was very widely used in the like PlayStation 1, PlayStation 2 era of games to map colors to do fake lighting. Basically light mapping, but without textures. They're also often used as masks for things because they are, again, 4 channels. So we can use them to blend between different textures. We can use them to create terrain shaders that blend between different kinds of terrain, right? There's also normal vectors, like I spoke about earlier. You don't have to use them as normals if you don't need to light your model. You can put any other data you want in there. Could be whatever you want. There some other lighting relevant data that is in the model as well, binormals, tangents, but those are automatically generated and not generally something you want to touch or are easy to touch or play with. All in all, that means that if you're making a mesh that's going to be light mapped, you still have at least 8 different float values to store a lot of fun stuff in. And for most use cases, you don't need nearly that much. So let's just do some examples. I'm going to show you some fun things that you can do just by storing a little bit of extra data in your models or textures. So let's start with a basic plant shader. Very wobbly plant. Oh, it's very dark. So say that you want to make a plant sway in the wind. You get some noise. Use it to rotate your plant model in the direction of the wind. Works just okay for simple grasses and plants, things that are very like one point. But imagine putting this on a tree. The entire thing would be swinging all over the place and it would look absolutely ridiculous. So we can start by saving this gradient of the model in the UVs. This is just basically the model projected from the side, saved into the UVs. So you have this grayscale value where the bottom is 0 and the top is 1. And if we use that to multiply the strength of the wind, we get this. And all of a sudden, you've just like stepped this up way more and you've barely changed the shader. The only thing we needed to do was project the model from the side in the secondary UV channel. But I don't think this is good enough. You can see that the wind barely affects the lower leaves, and it's kind of bending the top of the leaves that are arching. They're bending a lot more than the bottom leaves. It's looking a little strange. So if we add a little bit more data, we can do something even better. So in the order on the screen, this is the data that we're going to use next. Let's see if I can grab my mouse cursor here. There we go. This thing here, this is a random value from 0 to 1 assigned to each leaf on the mesh. We use this to offset where we sample the noise in the texture or in the model at the end, so that all the leaves don't move in unison, so you don't get the whole thing bending in one go. We also store a gradient. This is kind of similar to the first one here. We store a gradient that goes from 0 to 1 from the bottom of the leaf to the tip of the leaf, right? This is just slightly more complicated than the previous gradient, but it's essentially the same concept. And then there's this one. This is data stored in the vertex colors, unpacked the same way I unpacked the normals in the normal map section. It contains essentially a direction vector stored from the bottom of the plant to the tip of the leaf. And we use that to modulate the direction of the wind, or the wobble of the plant, so that it doesn't move if it's already pointing in the direction of the wind, right? Because there's nowhere for it to move. You apply all this data, you get this. A much more realistic plant movement, right? And the shader is not really much more complicated. It is really all in the data that we're using to animate it. This is one of my favorite techniques. If you use some scripting, I do not expect you to do this by hand. It's a lot of work if you were to be trying to do this. You can save the pivots of the parts of your model into the UVs of that model, right? Because your UVs have a bunch of float values. You save a position for the center of that piece of the model into those float values. You can use that pivot value to do all sorts of fun procedural animation in your shader. This is a technique that is used a lot in games nowadays. I imagine some of you have probably heard of Fortnite before. Yes, they use it as a shader on objects that you're constructing to make parts of that object fall from the sky or grow in when you're building it, right? That's all this is just storing that pivot at one point. You can go even more advanced then and start saving a hierarchy of pivots. You can save one pivot, you can save the identity or the ID of the parent of that pivot, and then save that parent's pivot, etc., and build this like tree of pivots. And you can use that to achieve things like advanced wind movement for trees. Then you're really starting to get into complicated math, but it's really just an extension of a very simple technique. And then we can take this to its absolute extreme. I don't really understand how this one works. It takes these three textures together with data stored in the model, and it controls positions and rotations of all the vertices in the model. Essentially, this is an entire animation of a fluid simulation that I exported from Houdini, and it's stored in these textures and in the model. There's no like actual animation in engine. There's no fluid sim being run. This is all done entirely in a shader. Complete magic. I have no idea how it works, but it's super cool. And so really, that's it. That's how you can take all the kinds of stuff that you can think about storing in your data, in your models and your textures. You can do all sorts of crazy stuff with it. It's time to stop thinking of them as just shapes and images, and it's time to start thinking of them as playthings to screw around with.